right. Okay, so what am I going to call this video? I think I'm going to name it The Case Against L'Hopital and The Case for L'Hopital. All right, so I think the College Board took L'Hopital out of its curriculum. Now that could be because they brought in slope fields and other things that they thought were more important, or maybe they made a philosophical decision not to use it for conceptual reasons. I land on the latter side of that argument. I don't like to teach L'Hopital to my calculus classes because I think it stands in the way and gets in the way of understanding one of the major concepts of a calculus course, which is the derivative. I think it takes away a very valuable discussion that I like to have throughout the semester. I'll point that out in a minute. But I am also a very big fan of the elegance of the conversion process in mathematics. I think you can look at that zeros and ones symbolic ruler video and you'll see why. I'm starting to think of polynomials in terms of the A term as an adjustment. I used to call it a multiplicative converter. I think I'm going to start calling it the adjuster and make a new video to simplify that process as well. But let's get at this video. And so I'm mixed. To teach it or not to teach it? That is the question. I'm a big believer that if you have a problem with something, you get rid of it. So I'm going to get rid of it. I'm going to show you why I don't think you should teach L'Hopital before I teach it. And then you can make the decision, not me, to continue watching the video or not, depending upon where you are in your calculus class. So I'm getting rid of the problem that way. To give you an idea of what I mean by getting rid of a problem, let's talk about high schoolers or middle schoolers who have trouble with fractions. All right, so I used to teach, and I'm just making this change now because of repetition. I used to teach addition of fractions using bingo, bango, bongo. Wasn't my good mathematician friend showed me that many years ago, and I thought it was very useful. Bingo, bango, bongo, right? So AD plus BC, BD. So if you were to add a third and a half, then it's 1 times 2 is 2, 3 times 1 is 3, 3 times 2 is 6. And I go like, yeah, okay, piece of cake. Simplifies the process. You don't have to, you show the longer process and then you take the shortcut. Okay, and in calculus, a lot of times you'll get f of b minus f of a and it's fractional. And nobody likes to deal with them. So it's a problem. What's the problem? Division by 4, division by 3, division by 2. Well, what gets rid of that? Multiplication by 24 certainly does. A little closer look, and so does multiplication by 12. So if you multiply by 12, you get 24, you get minus 33, you get minus 32, and you get plus 6. All right, that's not hard. You know, you got yourself 24 and 6 is 30, 30. Let's get rid of this. 30, where am I? 30 minus 65, negative 35, right? Didn't do anything hard, didn't have to think too hard. Oh yeah, I made it 12 times bigger. Geez, maybe my final answer should be 12 times smaller, and you're done. Right? I didn't feel any pain there. I didn't feel any stress around the problem. The problem disappeared, the divisions disappeared, then I brought them back. And so I got a problem over here. Do I teach L'Hopital or not? I mean, students use it all the time. You get a correct answer on a test, but did you learn anything? No, you just did something mechanical. And nothing wrong with that. You get some points on a test, great. See how many people, talk to how many people around you and ask, why does it work? Well, we'll look at that in a moment on the side. Okay, so a lot of you can do this from points of discontinuity for rational function. Okay, from that context, factoring, canceling the factors, that's fine. But what you're looking at really here is, from a calculus standpoint, is y equals x squared. You're looking at that function, then you're looking at y prime of 3. Okay? And I like to give different variations on this throughout the entire semester and have the discussion, the following discussion, which is, 3 gets you 9, right? So that's your x1, there's your y1, right? And then if you were to start, say at 7, 7 gets you what, 49. 40 divided by 4 is average rate of change of 10. You go to 6, you do the same thing, 36, you get an average rate of change of 9. You go to 5, you get an average rate of change of 8. You go to 4, you get an average rate of change of 7. I guess when you get to 3, you get an average rate of change of 6. If you were to pick a number like 3.001 and squared it, what we got, 9.006001 is what you get if you square that. And then you start talking about, the heft of this calculation, which is change in y, 0.006 over 0.001. And you can see the 2x derivative of x squared. Okay, I want to have that discussion. And if I do L'Hopital, I can't have it. All right, so that was a quick discussion. I don't know if I did a video on that earlier and really spelled that out more clearly and taking more time. Okay, but that's what you want to see. I mean, there's two big aspects of a calculus course, differentiation and integration. There's a major discussion here, major discussion. So is, the 3 plus h. 3 plus h as h goes to 0, as h goes to 0. Same discussion, except it's 3 plus h squared, right, over h. You want to be talking about that till students see it, right? And it doesn't come in initially. This is one of those situations that you got to spend time on as a teacher. All right, so your choice. If you're taking calculus, limits are done from a sequential standpoint for a couple of weeks, so you probably already encountered it even before you. No, you couldn't have done it from derivatives until you studied derivatives. So I guess I take that statement back. But these are the discussions I want to have. But let's go look at L'Hopital from the standpoint of the elegance of the conversion and why it works. Because it is a very pretty and simplistic calculation, and it deserves a little check for, oh, wow, somebody saw something that's kind of neat. All right, so let's look at the same problem. The limit as x goes to 3, x squared minus 9, x minus 3. All right, and I'm sure you're familiar if you've worked with L'Hopital. You plug in 3, you get 0 over 0, which means you can apply it. So what do those zeros mean? X minus 3 is a graph, right? It intersects at 3, 0. So you put a 3 in, it's a 0. It's right there. X squared minus 9 is a graph. Well, I guess you can see this. No, it also goes 3, 0, which I guess means that you got a point of intersection. Point of intersection, right there. I boxed it. All right, there's your 3, 0 right there. All right, and so I'm going to start to zoom in on this. I'm going to start to, Desmos, you can use Desmos and zoom in on it. And if you zoom in on it, you start to linearize it. Those curves start to disappear and you start to see straight lines. And the more times you zoom in, I'm going to zoom in 10 times. I'm going to get a 10 times closer look here. I'm going to get 100 times closer look here. I'm going to get 1,000 times closer look here. And if you do that on Desmos, that picture never changes. Never changes. All right. I encourage you to play with it. Just keep zooming in on the same place. That's what it looks like. Okay. Now I'll extend this. Let's see if I can do this. Extend it, extend it, extend it. I might be looking from 3 to 3.01. Same picture. So let's put a dotted line there because that is the y value of the denominator. This is the y value of the numerator. Okay? And I'm just going to highlight this over here. I'm going to highlight the triangle over here. That appears to be a change. That's a y value. How about I call it rise? How about I call it run? Rise over run. Yeah. Slope of this line. Oh, is 1 to 1. But anyway, the rise over run of that triangle is the y value of the denominator divided by the change in x. Let's make sure you can see that. That's all. I'm just going to call this the y of the denominator. This is the x squared minus 9 function that's been linearized. So I'm going to call that the y value of the numerator. And it's over, oh, you know what? They share. They share this change in x. Wow. Wow. And rise over run, I think that's the slope of the tangent. I think this is actually the tangent. Well, of course, it's its own tangent, the linear. But I think over here, I have actually created the tangent slope to this curve right here. Can you see that? Yes. Yeah, I'm looking at that tangent line. I'm really looking at that tangent line right here. Right? And that's its own tangent, x minus 3. Right? So I'm looking at slope. The slope of one divided by the slope of the other, well, those cancel. Right? When you do that division. So I'm looking at the rate of change of the quadratic divided by the rate of change of the linear function. It's getting me my division. It's getting my division. The value of that division at 3. That's why L'Hopital works. Okay, now I just did this on the fly. 10 minutes ago I was thinking about it. Do I want to show that or not? So again, all the videos I'm making probably could say things more succinctly and probably organize them better. But I'm trying to put some of this stuff down just so a class can think about it. So I'm going to upload it. All right. So much for that. Hope everybody's doing well in these trying times.